In the rhythm of numbers and the melody of arrays, we seek patterns hidden in subtle ways, where two paths of order meet side by side, their growth in harmony we cannot hide. Today we unfold a tale within the code of sequences increasing in a structured mode. Welcome to the exploration of adjacent increasing subarrays detection, the second problem, where mathematics and logic dance together in elegance. We are given an array of integers called nums. Our goal is to find the largest integer k such that there exist two adjacent subarrays, each of length k, and both are strictly increasing. Adjacent means one ends exactly where the other begins. We must return this maximum possible value of k. Let's see an example. For the array 2, 5, 7, 8, 9, 2, 3, 4, 3, and 1, we find that 7, 8, 9 is strictly increasing, and the next subarray 2, 3, 4 is also strictly increasing. They are adjacent, each of length 3, hence the answer is 3. Another example 1, 2, 3, 4, 4, 4, 4, 5, 6, and 7. Here the sequences 1, 2, and 3, 4 are both increasing and they are right next to each other. Both have length 2, so the maximum value of k is 2. Let's look at some important insights. A strictly increasing subarray means that each element is greater than the one before it. To detect adjacent increasing subarrays, we focus on the boundary where one increasing run ends and another begins. For each position I, we can record left I, the length of the increasing sequence ending at index I, right I, the length of the increasing sequence starting at index I. At the junction between them, the possible k is the minimum of these two lengths. The approach is simple and efficient. Step 1. We compute left I, the increasing run ending at each position. Then we compute right I, the increasing run starting at each position. For every boundary between elements, find the smaller of left I and right I plus 1. We take the maximum of these values. That gives our answer. This algorithm runs in big O of n time and uses big O of n space. Let's walk through an example step by step. For the array 2, 5, 7, 8, 9, 2, 3, 4, 3, and 1, the left array records increasing lengths ending at each index. The right array records increasing lengths starting at each index. When we compare boundaries at index 4, minimum of left 4, right 4 equals minimum 5, 3, which is equals to 3. That's our maximum k. So the final answer is 3. Here is the C++ implementation. We use two vectors left and right, both initialized with 1s. We make one forward pass to fill left values and one backward pass to fill right values. Then we compute the maximum of min left I, right I plus 1 for all valid indices. This simple linear time solution elegantly captures the problem's essence. Let's analyze the performance. The algorithm scans the array twice, hence once forward and once backward. Therefore, time complexity is big O of n. We store two helper arrays making space complexity big O of n. This makes the approach fast and scalable, even for inputs up to 200,000 elements. Let's recap what we have learned. We explored a problem where two adjacent increasing subarrays coexist. Using pre-computed lengths of increasing runs, we identified their optimal boundary efficiently. The key idea was finding the maximum of the minimum lengths around each split point. Our final algorithm is elegant, efficient, and easy to implement. This is adjacent increasing subarrays detection, the second problem, where simplicity meets brilliance in algorithmic design.